Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module Antiferro and Ferri-magnetism, Magnetostriction and its frequency dependence from the paper Functional Materials. So main points which will be covered in this module are: first, antiferromagnetic materials with detailed description of 100 plane view of manganese oxide lattice. Second, ferrimagnetic materials along with some examples are discussed in this module. Third, magnetostrictive effect. Magnetostriction in nickel and iron is explained. Magnetic losses and frequency dependence of permeability is also explained in this module. So students, let us start with some brief introduction about this module. Antiferromagnetism involves the materials in which the atoms or the ions or the molecules having a permanent dipole moment, which is basically resulting from unpaired electron spins, as in the case of paramagnetic and ferromagnetic materials. And the crystals, they have the domain structure as in the case of ferromagnetic materials. But alternating ions within a domain have their magnetic moments oriented in the opposite directions. So, the domain as a whole has zero magnetization, or we can say zero susceptibility. So students, let us consider an example of an antiferromagnetic material, which is manganese oxide. It has been discussed in detail later on, in which the Mn2 plus ion has a magnetic moment. Such materials are generally antiferromagnetic at lower temperatures. As the temperature is increased, the domain structure breaks down and the material becomes paramagnetic, as it also happens, of course, with ferromagnetic materials. But whereas the susceptibility of a ferromagnetic material decreases dramatically with rising temperature until it becomes merely paramagnetic. The susceptibility of an antiferromagnetic material starts at 0 and its transformation to a paramagnetic material results in an increase in its susceptibility. As the temperature is raised still further, the paramagnetic susceptibility drops, as is usual for a paramagnetics. So there is presumably some temperature at which the susceptibility is maximum. Antiferromagnetic materials The antiferromagnetic materials are those materials in which the electron spins associated with the magnetic atoms at a particular crystallographic sites are ordered yet oriented with respect to each other in such a manner that their net magnetization is equal to 0. This is the case below a particular temperature called as Néel temperature, which is denoted by T suffix n, above which the material behaves as a paramagnet. Examples include the metallic manganese, chromium, various transition metal oxides such as manganese oxide, forms of iron oxide, multiferroic perovskites like bismuth ferrite. Now students, here you can see the structure of two materials, that is manganese oxide and manganese fluoride. In manganese oxide, since oxygen is not a magnetic ion, the anti-parallel spin arrangement of Mn2+, the magnetic ion, in two sides gives rise to zero magnetization. Now the figure shows the structure of manganese oxide drawn on 100 plane. Here you can see the dark dots showing the spin up and the shadowed dots showing the spin down. These are nothing but the 100 planes consisting of manganese oxide atoms. Notice the opposite spins on the two parallel planes. Here the shadowed and the dark dots show the manganese ions or manganese atoms, and the hollow dots shows the oxygen atoms. Now let us discuss about the temperature dependence for the susceptibility for antiferromagnetic materials, which is governed by the Curie-Weiss law. The susceptibility of an antiferromagnetic material, a paramagnetic behavior, is exhibited above Tn, which is clearly evident from the figure, and between 0 Kelvin and Tn, it shows the antiferromagnetic behavior. Antiferromagnetic materials are not very useful because they do not show any magnetization whatsoever. As evident from the figure above Tn, the susceptibility variation with temperature obeys the Curie-Weiss law. Some of the materials, like bismuth ferrite, have been described as canted antiferromagnets, where spin of atoms are not exactly antiparallel but are slightly inclined towards the so-called parallel axis, which may give rise to very small magnetization. Now students, let us discuss another category of magnetic materials, that is ferri-magnetic materials. These are the materials which, again, like antiferromagnetic materials, shows anti-parallel alignment of moments at particular atomic sites, that is, magnetic moment of one crystal sublattice is anti-parallel to the other. But since most of these materials consist of cations of two or more types, sublattices contains two different types of ions with different magnetic moment for two types of atoms, and as a result, the net magnetization is not equal to zero. The examples of such materials are various kinds of cubic spinel ferrites such as nickel ferrite, cobalt ferrite, ferrite that is Fe3O4, copper ferrite, etc. Other examples are hexagonal ferrites, that is, for example, the BaFe12O19 garnets such as Y3Fe5O12, which is represented by a general formula R3Fe5O12, where R, in addition to yttrium, can be one of the lanthanide atoms such as lanthanum, cerium, samarium, etc. This shows the schematic representation of this inequality in the neighboring magnetic moment. As we can see from the ferromagnetic materials, all the magnetic moments they are aligned in the same direction, whereas in the antiferromagnetic materials, the spins they are alternately oppositely aligned. But in the case of ferrimagnetic materials, they are anti-parallel alignment of moments, but the magnitude of the moments is not equal. Now we will study about the temperature dependence for the ferrimagnetic materials. The ferrimagnetic materials also follow a temperature dependence of magnetization and susceptibility near Curie transition, which is actually Neal transition, in a similar manner as shown by ferromagnetic materials. These materials, like ferromagnetic materials, shows significantly large magnetization below the magnetic transition temperature, and hence often the temperature dependent behavior is clubbed with that of ferromagnetic materials. As we can see from the figure that below the critical temperature or the Curie temperature, it shows the ferrimagnetic behavior, and above the Curie transition temperature, it shows the paramagnetic behavior. Above figures shows the tetrahedral and octahedral sites in spinel ferrites. Here we can see the two examples of ferrimagnetism, that is the nickel atom and the iron atom. As we can see, we have the A site shown by the 8Fe3+, which is having the electronic configuration as 3d5. All the spins are parallel to each other, whereas at the B site, that is 8Fe3+ and 8Ni2+, the spin or the moments, they are antiparallel. The inverse spinel is also shown by NiFe2O4, that is the net magnetic moment of 2 μb is obtained for nickel ferrite. So students, till now we have learned that there are 4 kinds of magnetism, that is diamagnetism, paramagnetism, ferromagnetism, and ferri and antiferromagnetism. The field dependent magnetization behavior of these different types is shown in the figure, as well as the temperature dependence for the susceptibility is also shown. Diamagnetism is the basic character which is present in every material. It is just that this behavior is overshadowed in materials where other effects are present too. As we can see from the figure showing the variation of susceptibility versus temperature, the black curve shows the variation for antiferromagnetic materials, the green shows the variation for paramagnet, and the red one shows the variation for the ferromagnetic materials. Practically, most important materials are ferromagnets, which are mostly metals, and ferri-magnetic materials, which are mostly ferrite oxides, which will be discussed in the subsequent sections. Magnetic losses. Hysteresis loss is the energy loss per cycle times the number of cycles, and it is given by pH equal to 2 multiplied by F multiplied by Hc multiplied by Br, where F is the frequency of applied field, Hc is the coercive field, and Br is the magnetic remanence. Next parameter is the eddy current power losses, which can be expressed by Pe is equal to pi d square by 6 rho, the whole multiplied by F multiplied by B max. Next, we will study about the frequency dependence. Domain wall movement is dependent on the frequency of applied field. In some materials, low frequencies are needed for easy switching, while some materials can witness easy switching at gigahertz or microwave region, frequencies which makes them suitable for microwave devices. In the AC field, which can be expressed as H is equal to H naught exponential iota omega t, B is equal to B naught exponential iota omega t minus delta. So, the complex permeability can be expressed as mu as a complex quantity given by mu prime minus iota mu double prime, and the loss tangent by tan delta is equal to the ratio of the imaginary part, that is mu double prime, divided by the real part, that is mu prime. Now students, let us discuss about the magnetic losses and the frequency dependence. This is important mainly for ferromagnetic and ferri-magnetic materials when they are placed in an alternating magnetic field. Associated with frequency response are magnetic hysteresis losses and frequency response of magnetic permeability. So first we will start with magnetic losses. So we imagine a ferromagnetic or ferri-magnetic material with a hysteresis curve which is subjected to an alternating magnetic field represented by H is equal to H naught exponential I omega t. The frequencies are kept typically low such that the switching of magnetization of the material keeps pace with the magnetic field switching. In an analogy to the dielectric materials, two loss mechanisms are of importance. First is eddy current losses induced by the alternating magnetic field, which are quite dependent on the resistivity of the material. And secondly, the domain wall motion requires as well as dissipates some amount of energy, resulting in what are called as intrinsic magnetic losses or hysteresis losses. Both of these effects add up and energy loss is dissipated as heat, while frequency, magnetic field strength, and maximum magnetic flux increase both types of losses, increasing the resistivity ρ and decreases the eddy current losses in particular. Losses are more when material is conducting, and many ferromagnets tend to be quite conductive. Now, first let us discuss about the hysteresis loss. Hysteresis loss is energy loss per cycle times the number of cycles and is given by P suffix h is equal to 2F HCBR, where F is the frequency of the applied field, Hc is the coercive field strength, and Br is the magnetic remanence. Next is eddy current power losses, which can be expressed as Pe is equal to pi d square by 6 rho, the whole multiplied by F multiplied by B max. Now the total power loss is the sum of these two losses. These two equations can help a user to choose a material carefully so that the losses can be minimized. Frequency response of permeability. Given that the ferro and ferri-magnetic materials have permanent moments which constitute the regions of aligned moments called as domains, with two regions of different regions separated by a domain wall. Now, ease of domain wall movement can be described in terms of coercivity. That is, lower the coercive field, easier it is for the domain walls to move during switching. So, all we can say at this point is that this domain wall movement is dependent on the frequency of the applied field. In some materials, low frequencies are needed for easy switching, while some materials can witness easy switching at gigahertz or microwave region frequencies, making them suitable for microwave devices. This also means that the permeability, that is mu, in a similar manner as permittivity in dielectrics, which can be defined as a complex quantity, that is mu is equal to mu prime plus iota mu double prime, where mu prime is the real part of permeability and mu double prime is the complex part of permeability. Now let us discuss about the frequency response of permeability. While at low frequencies in a linear magnetic material, that is B, is equal to mu naught mu r h. At high frequencies, these two parameters are related to each other with some time lag. These fields can be written as phasors such that h is equal to h naught exponential iota omega t and b is equal to b naught exponential iota multiplied by omega t minus delta, where delta can be expressed as the phase delay of b and h. Now we can define the magnetic permeability as mu is equal to b by h. Now taking the ratio of b by h, that is b naught exponential iota omega t minus delta divided by h naught exponential iota omega t, it gives b naught by h naught exponential minus iota omega. This equation clearly states that the magnetic permeability is a complex quantity. Now further simplifying the above equation, we get mu is equal to b naught by h naught cos delta minus iota b naught by h naught sin delta. This is equal to mu prime minus iota mu double prime. This shows that mu is a complex quantity but with a negative complex part. Hence, the loss tangent is defined as the ratio of the imaginary to the real part of the complex permeability. Hence, we can say that tan delta is nothing but the ratio of mu double prime divided by mu prime. The loss tangent is representative of the how much power is lost in a material versus how much power is stored. The piezo-magnetism. Students, here we will be discuss the magnetostrictive effect in detail. As we can see from the figure, a saturation is achieved upon reorientation of all the domains, and it has been shown in the figure for nickel and iron. These are the best examples for magnetostriction, that is nickel and iron. This rotation and reorientation of domains causes development of internal strains in the material. Depending on whether the magnetostriction is positive or negative, the microstrains generated in the materials lead to the either of stretching or contraction of the material along the direction of the magnetic field, while these may also lead to small changes in the volume of the material. It is typically assumed to remain constant under normal operating conditions. The reason of why the domain rotation upon the application of the magnetic field results in a change in the dimensions of the material lies in the magnetocrystalline anisotropy. Because of anisotropy in the magnetic behavior of material, the energy to magnetize a crystalline material in one crystallographic direction may be different than in the other direction or the order direction. So when a magnetic field is applied to a material, the structural rearrangement in the material tends to happen in such a fashion so that an easy axis aligns itself with the applied magnetic field, leading to the minimization of the free energy of the system. As a result, the strain is generated in the materials as different crystallographic directions have different lengths and magnitudes. The materials also exhibit a reciprocal effect when the application of a mechanical stress results in a change in the magnetic susceptibility of a material, and the resulting effect is called as the Villary effect, which is depicted by the change in the sign of magnetostriction. For example, in iron, it changes the sign from positive to negative when iron is subjected to a field strength of 40,000 ampere per meter. There are two other effects which are related to magnetostriction. The first one is Mathieucki effect, in which the magnetic susceptibility has the helical anisotropy when a mechanical torque is applied to a material. The second effect is called as Weidemann effect, in which the materials exhibit the twisting when subjected to a helical magnetic field. In general, magnetostriction can be viewed as a coupling between the mechanical and magnetic orders or the degree of freedom. Hence, the effect can be considered in which reversible exchange of mechanical and magnetic energy happens. This conversion of energy from one form to the other makes these materials very attractive for the use in actuator and sensor applications. Similar to the flux density, magnetostriction also exhibits a hysteresis when a material is swept under a varying magnetic field. The shape of such a hysteresis loop is like a butterfly loop as observed in piezoelectric materials. So, the inverse of the piezomagnetism is called as the magnetostrictive effect. Magnetostriction. Magnetostriction is a property of a ferromagnetic material that causes them to change their shape or dimension during the process of magnetization. The variation of materials magnetization due to the applied magnetic field changes the magnetostrictive strain until reaching the saturation value, that is lambda. This effect was first identified in 1842 by James Joule when he was observing a sample of an iron. The examples of magnetostrictive materials or ferrites. Since magnetostrictive materials allows one to convert the magnetic energy into mechanical energy, such as kinetic energy or vice versa, where one can use the reverse effect to generate the magnetic energy. These are used to build variety of useful devices, for example, in actuators and sensors. One can define the magnetostrictive characteristics of a material by a magnetostrictive coefficient, that is lambda, whose value may be positive or negative. The value of lambda is a measure of the fractional change achieved in dimension, example length, when material's magnetization varies from 0 to a saturation value. One often hears a humming noise near the magnetic devices, for example, transformers and high power electrical devices, called as electric hum, which is caused by this effect only. The following table shows the magnetostriction constants of some ferrite. It also shows the saturation magnetostriction, that is lambda bar, for polycrystalline materials, which is calculated from these constants. Note that these values are for room temperature. So, all the compositions, we have a specific lambda, or we can say the magnetostrictive coefficient, which is positive for some materials and is negative for the other materials. As noted from the table, the lambda 100 is negative for all the ferrites, whereas the lambda 11 is positive for mostly materials, but it has the negative value for Ni 0.8, Fe 2.204 and Mn 0.98, Fe 1.8604, and the lambda bar, which is nothing but the saturation magnetostriction, is also positive and negative for these materials. As we can see from the figure, which shows a hysteresis loop, this is like a butterfly loop as observed in piezoelectric materials. This graph is shown for manganese zinc ferrite, and this has been taken from Wikipedia. Among pure elements, cobalt exhibits the largest room temperature magnetostriction of approximately 60 microstrains. During Second World War, nickel was used as a magnetostrictive material in early sonar transducers, which was later substituted by an iron-aluminium alloy due to shortage of nickel. One of the best known engineering materials showing very high magnetostriction coefficient is terphenol D. Terphenol D exhibits the magnetostriction of approximately 2000 microstrains at room temperature in a field of 2 kilo-oersted. Another common magnetostrictive composite is an amorphous alloy of iron, silicon, boron, and carbon with a chemical formula of Fe81, Si 3.5, B 13.5, C2. This is also known by the trade name Metglass 2605SC. It exhibits the magnetostriction value of 20 microstrains at saturation. Metglass possesses very low magnetic anisotropy, requiring field strength of less than 1 kiloampere per meter for magnetic saturation. Various ferrites also show magnetostrictive behavior. For example, Fe3O4 shows a magnetostriction coefficient of about 25 microstrains whose sign is reversed with cobalt and nickel doping with CO.8 Fe2.2O4 showing a value of minus 210 microstrains and CO.8 Fe2.2O4 showing a value of minus 40 microstrains. So students, let us summarize what we have learned in this module. First, we have discussed about the antiferromagnetism. Antiferromagnetism is also another example of magnetic ordering with oppositely oriented spins leading to complete cancellation of magnetic moments. Second, these materials are characterized by a Néel temperature, which is represented by Tn, below which they remain antiferromagnetic and are paramagnetic at a temperature greater than Tn. Third, another form of antiferromagnetism is observed in Ferri-magnetism, albeit with incomplete cancellation of spins due to unequal magnitude of spins on different sublattices. As a result, ferromagnetic materials shows a behavior similar to the ferromagnetic or the ferrimagnetic materials. They are similar to ferromagnetic materials. Next, that the magnetic materials which exhibit the magnetostriction, they manifested by the development of the strain when the material is magnetically switched. This is a very useful phenomena and it is employed in various applications such as sensors, actuators and transducers. Magnetic materials are also affected by the frequency of the applied magnetic field, with the loss tangent being a signature of the power loss. Thank you.